All right, everyone. So here we are in the final section for chapter 4. Chapter 4, section 3. This is distinguishing among atoms. All right, so we walked a lot through history on how we got to the atom and the atomic model. We have a couple other people to talk about. Henry Moseley was a colleague of Rutherford who we used his main atomic model. And he found that every element had a unique charge in its nucleus. And he determined that the number of protons in an atom identifies it as an atom of that particle. So then we get to this word atomic number. Every element has an atomic number, and that is equal to the number of protons. That is super important to remember. Each element's atomic number is equal to the number of protons in its nucleus. In a neutral atom, for example, that has no charge, the number of protons will actually also equal the number of electrons, because the number of protons, being positive, need to be completely neutralized with the negatively number of electrons. So that's really important also to remember. So the atomic number is equal to the number of protons, but if that atom is neutral, there's no charge to it, meaning it won't be an isotope. We'll talk about what that name means. The number of protons will equal the number of electrons because it's totally neutral charge. So the number of positive charges cancels out the number of negative charges. So the number of protons cancels out the charges of the number of electrons. So those will be totally equal. Number of protons equals number of electrons in a neutral atom. Let's do a sample problem that talks about understanding the atomic number. The element nitrogen with the atomic symbol uppercase N has an atomic number of 7. How many protons and electrons are in a neutral nitrogen atom? Let's analyze, identify the relative concepts. The atomic number gives us the number of protons, which in a neutral atom will always equal the number of electrons. So we'll apply the concepts, identifying the atomic number, and then using the atomic number to find the number of protons and electrons. The atomic number of nitrogen is 7. So a neutral nitrogen will have 7 protons and 7 electrons. You'll be doing a lot of practice problems like this week. Dalton stated that all atoms of an element are identical. The same element have different masses. What subatomic particles make up the mass of an atom? We talked about in section 4.2 that the number of protons and the number of neutrons really make up the atomic mass of an atom, because the electron's mass is so little, it's practically nothing. The mass of an electron is negligible. So then the mass number. The mass number is equal to the number of protons plus the number of neutrons. If you know the atomic number and the mass number of an atom of any element, you can determine the atom's composition. Because the number of neutrons, you would just take the mass number minus the atomic number, and we'll go over a lot of practice problems. So let's determine the composition of an atom. How many protons, electrons, and neutrons are in each atom? Let's talk about, this is beryllium, neon, sodium. So I'm just going to go back. So we're going to kind of do 3 practice problems here. We're going to look for the number of protons, electrons, and neutrons in each of these 3 atoms. The number at the top is always the mass, and we determined previously that the mass number is equal to the number of protons plus the number of neutrons. So I'm just going to go ahead. So this is the mass number, is always the number at the top, and the atomic number is always the number at the bottom. And the atomic number is always equal to the number of protons and electrons in a neutral atom, and the mass number is always equal to the number of protons and neutrons, because those are the subatomic particles that make up the mass. Okay, so let's go through the first one. Let's analyze the knowns. Beryllium has an atomic number of 4 and a mass number of 9. Neon has atomic number of 10 and a mass number of 20. and sodium has the atomic number of 11 and the mass number of 23. Remember, atomic numbers are always equal to the number of protons and electrons in a neutral atom, and the mass number is always equal to the number of protons and neutrons, because those are the particles that have mass. All right, so let's go ahead and solve this. Solving for the unknowns. The atomic number gives us the number of protons. That's one is easy. So if the atomic number is 4, that atom will have 4 protons. And if the atomic number is 10, it will have 10 protons. And if the atomic number is 11, it will have 11 protons, because the atomic number always gives us the number of protons. Using the atomic number to find the number of electrons. The atomic number also gives us the number of electrons in a we'll have 10 electrons, and if it's 11, we will have 11 electrons. Remember, electrons equal the atomic number when the atom is neutral. It gets a little tricky when the atom is not neutral, and we'll talk about that later. Then we'll use the mass number and the atomic number to find the number of neutrons. We know that mass is equal to the number of protons and neutrons, so we'll find the number of neutrons by subtracting the protons from the mass. So the number of neutrons would be the mass number minus the atomic number. So 5 neutrons, 20 minus 10 is 10 neutrons, and 23 minus 11 is 12 neutrons for the last. The results make sense. For each atom, the mass number equals the number of protons plus the number of neutrons. So that makes sense. Let's move on to isotopes now. There are 3 different kinds of neon atoms. And how do these atoms differ? They differ in their number of neutrons, as shown here, and that makes them isotopes. So when atoms differ by their number of neutrons, that will make them isotopes. This is called neon 20 because the mass is 20. Take 10 protons plus 10 neutrons is equal to 20. Neon 21, the mass number is 21 because it adds an extra neutron to it. 10 plus 11 is 21. The isotope neon 22 still always has the same number of protons, but just has different numbers of neutrons. So in order to determine isotopes, isotopes will have different numbers of neutrons in their nucleus. So it'll affect the mass number. Isotopes are atoms that have the same number of protons, but different numbers of neutrons. So neon 20, 21, and neon 22 are 3 isotopes of the atom neon with different numbers of neutrons, respectively, so it will have slightly different mass numbers. Because again, neutrons will determine the mass. Because isotopes of an element have different numbers of neutrons, they also have different mass numbers. Isotopes are chemically alike because they have identical numbers of protons and electrons still, which are the subatomic particles responsible for chemical behavior, but the number of neutrons in isotopes does not change which element it is because the atomic number does not change. So the number of neutrons doesn't change the type of element or atom it is because the chemical properties and behavior of an atom are determined by the numbers of electrons and protons. So isotopes are purely based and are atoms based on the number or differences in neutrons. So let's go over another sample problem. I really like how this textbook and these PowerPoints give you lots of sample problems and lots of practice. So diamonds are a naturally occurring form of the elemental carbon. 2 stable isotopes of carbon are carbon-12 and carbon-13. So those are 2 different isotopes, meaning they're just going to be differing in their number of neutrons. Write the symbol for each isotope using superscripts, subscripts to represent the mass number and the atomic number. So identify the relevant concepts. Isotopes are atoms that have the same number of protons, different number of neutrons. So the composition of an atom can be expressed by writing the chemical signal, that's the letter abbreviation, and then the atomic number as the subscript, that's the number on the bottom. That's always the atomic number equaling the number of protons. And the superscript is the mass number. That is equal to the number of protons and the number of neutrons. Use the periodic table to identify the symbol and atomic number for carbon. So let's take out our periodic table, which you can search anywhere on Google or use the one in the textbook. So the symbol for carbon is C, and the atomic number of carbon is 6. Look at the name of the isotope to find the mass number. So carbon-12, the mass number will be 12. And for carbon-13, the mass number will be 13. So we're going to write out these atoms. Using the symbol, atomic number, and mass number, write the symbol for each isotope. So for carbon-12 and for carbon-13, they would look like this. Carbon-12, we put the mass number at the top. That's the mass number. And 6 is the atomic number. And for 13, we just put a 13 as the superscript on the top for the mass number and a 6 on the bottom because the atomic number doesn't change at all. So what's changing here between carbon-12 and carbon-13? They're isotopes, so just the number of neutrons. So the number of protons, the atomic number is staying the same, but the mass number is changing. In carbon-12, it has 6 neutrons, and carbon-13 has 7 neutrons. We know that the number of protons plus the number of neutrons contributes to the mass of the atom. However, if you look at the periodic table, you will notice that the atomic mass is never a whole number. So you can see here, these are all the atomic masses, and they're never quite exactly whole numbers, or they have 4 significant figures. So what's going on with that? Each element has at least 2 naturally occurring isotopes. So the atomic mass actually takes into account the masses of each isotope. So here we have chlorine. We have the weighted average mass of chlorine. We're taking the total number of protons in 3 chlorine atoms and 1 chlorine 37 atom, plus the total number of neutrons in those 4 chlorine atoms. And we're getting an average weighted mass of a chlorine atom. So that's why the atomic mass unit or atomic mass of these elements is not the totally whole number, because we're taking the weighted average of those different isotopes. The atomic mass of mass reflects both the mass and the relative abundance of those isotopes as they occur in nature. So we're going to give preference to the elements that occur more abundantly in nature when calculating the weighted average mass. The isotopes of an element are not naturally present in equal quantities, thus we have to consider their relative abundance. Otherwise, the percentage that they will actually exist in nature. So here we get magnesium 24, 25, and 26. Magnesium 24 is more abundant in nature, so that we'll use that to calculate magnesium's atomic mass. What is AMU? This is the unit assigned to the atomic mass of an atom. It is based on the mass of a carbon-12 atom, and an atomic mass unit, AMU, is defined as 1/12 the mass of a carbon-12 atom. Masses of protons and neutrons are so incredibly small, so instead of working with these really small numbers, scientists agreed to use carbon-12 as the standard and assigned its mass as exactly 12 atomic mass units. So let's look at this in another sample problem, as we can see here. The atomic mass of copper is 63.546 atomic mass units. Which of copper's 2 isotopes is more abundant, copper 63 or copper 65? The atomic mass of an element is the weighted average mass of the atoms in a naturally occurring sample of that element, and we'll compare the atomic mass to the mass of each isotope. So the atomic mass of 63.546 is actually closer to 63 than it is to 65. So because of that, determine the most abundant isotope based on which isotope's mass is closest to that atomic mass unit. Because the atomic mass is a weighted average, copper-63 must be more abundant than copper-65 because the atomic mass unit is closer to copper-63. You can determine the atomic mass based on relative abundance, and to do this, you must know three things: the number of stable isotopes, the mass of each isotope, and the natural percent abundance of each isotope. To calculate the atomic mass of an element, multiply the mass of each isotope by its natural abundance expressed as a decimal. You get that from the percent, and then add up all the products. And I think we'll go through an example. So the average atomic mass would take the mass of isotope 1 times its abundance plus the mass of isotope 2 times its abundance. So let's go through a sample problem calculating the atomic mass. Element X, for example, has 2 naturally occurring isotopes. The isotope with a mass of 10.012 has a relative abundance of 19.91%, and the isotope with a mass of 11.009 has a relative abundance of 80.09%. So let's calculate the atomic mass of element X. The mass of each isotope contributes to the element's atomic mass, and it can be calculated by multiplying the isotope's mass by its relative abundance, and the atomic mass of an element would be the sum of those products. So we have the isotope, the mass, and the relative abundance, which we just need to change into a decimal. And then 11, we have the mass and relative abundance that we change into the decimal. We're looking for the atomic mass of X. So let's plug it into our calculator. We'll take 10 times the abundance to get this atomic mass unit for this isotope 10. And then for isotope 11, we'll multiply its atomic mass by its abundance to get this atomic mass unit. We'll add those together then to get the atomic mass. So add the atomic mass contributions together, and then we get the atomic mass unit of 10.810. Does the result make sense? The calculated value is closer to the mass of that more abundant isotope, so it does make sense. All right, that ends us through the chapter 4. Please work through these practice problems in your textbook, the worksheet I gave you, and let me know if you guys have any questions, because your test will be really heavy on problems like this. Good luck, everybody.